In March 1954, President Dwight Eisenhower sat in the Oval Office staring at a problem that kept him awake at night. The Soviet Union had detonated its first hydrogen bomb 4 months earlier, and American intelligence couldn't tell him how many bombers they had, where their airfields were, or whether an attack was imminent. The CIA's best estimates ranged wildly. Some analysts claimed the Soviets possessed 50 long-range bombers capable of reaching American cities. Others insisted the number exceeded 400. Nobody actually knew. The Pentagon was flying blind, quite literally. Traditional reconnaissance aircraft couldn't penetrate Soviet airspace without being shot down. The Boeing RB-47 Stratojet, America's primary spy plane, cruised at 40,000 feet, well within range of Soviet MiG-17 fighters and surface-to-air missiles. Several RB-47s had already been intercepted near Soviet borders, their crews killed or captured. Each incident pushed the superpowers closer to open war. Eisenhower understood aerial reconnaissance from his years commanding Allied forces in Europe. He'd seen firsthand how reconnaissance photographs before D-Day had revealed German defenses, saved thousands of lives, and turned the tide of battles. But in 1954, the Iron Curtain wasn't just political metaphor, it was an actual intelligence blackout stretching from East Germany to the Pacific Ocean, concealing roughly 1/6 of the Earth's land surface. The Air Force proposed a solution: develop a new reconnaissance aircraft that could fly higher than Soviet interceptors could reach. The magic number was 70,000 feet, more than 13 miles up, where the sky turns purple-black and pilots can see the curvature of the Earth. At that altitude, existing Soviet fighters simply couldn't function. Their engines would flame out in the thin air, and their airframes would stall long before reaching that height. But here's what made the requirement seem impossible. The aircraft couldn't just reach 70,000 feet for a few seconds like a rocket. It needed to cruise at that altitude for hours while carrying heavy cameras with long telephoto lenses. It needed fuel capacity to fly from bases in Western Europe deep into Soviet territory and back, round trips exceeding 4,000 miles. And it needed to be operational within 2 years, not the typical decade required for new aircraft development. The Air Force issued classified proposals to major aircraft manufacturers in late 1953. Bell Aircraft proposed a design, so did Fairchild and Martin. Each submission landed on the desk of Trevor Gardner, special assistant to Air Force Secretary Harold Talbot, who found them all inadequate, too heavy, too slow, too complex, too expensive. None could meet the altitude requirement while carrying sufficient fuel and camera equipment. Gardner was about to recommend scrapping the entire program when a colleague mentioned that Lockheed Aircraft Corporation had been working on high-altitude research projects. Lockheed wasn't even on the official bidder list, but Gardner knew their reputation. More specifically, he knew about Clarence Kelly Johnson, the legendary engineer who designed the P-38 Lightning fighter and the F-80 Shooting Star, America's first operational jet fighter. On a cold morning in early 1954, Gardner picked up a secure telephone and placed a call to Burbank, California. What happened next would change aerial reconnaissance forever, spawn a design philosophy that influenced aviation for generations, and create an aircraft so successful it would still be flying combat missions 7 decades later. Kelly Johnson was 43 years old in 1954, already a legend in aviation circles, but still hungry for impossible challenges. Born to Swedish immigrants in Michigan, he'd clawed his way from poverty to become Lockheed's chief engineer through pure brilliance and relentless work ethic. His office in Burbank overlooked the production floor where workers assembled Lockheed Constellation airliners. Beautiful aircraft, profitable aircraft, but nothing that made Johnson's pulse race anymore. The call from Trevor Gardner changed everything. Gardner wanted Johnson in Washington immediately for a classified briefing. No details over the phone. Johnson caught a red-eye flight that night. Inside a windowless Pentagon conference room the next morning, Johnson learned the parameters. The Air Force needed an aircraft capable of sustained flight at 70,000 feet with a range of 4,000 miles while carrying a 700-pound camera payload. Maximum weight, 16,000 pounds, less than half what conventional aircraft of similar range typically weighed. Time frame, operational capability by 1956, and the kicker: the Air Force had already rejected proposals from Bell, Fairchild, and Martin as technically unfeasible. Johnson asked for the rejected proposals. He spent 3 hours reading them in that conference room, and he immediately saw why they'd failed. Each company had essentially tried to modify existing aircraft designs, adding bigger engines, longer wings, and heavier structure. That approach guaranteed failure. You couldn't build a 70,000-foot reconnaissance aircraft by incrementally improving a conventional airplane any more than you could build a submarine by making a car watertight. The solution required radical thinking. Johnson opened his notebook and started sketching. Forget everything conventional about aircraft design. Start with pure physics. At 70,000 feet, air density drops to roughly 1/5 that of sea level. That meant two things. Wings needed enormous surface area to generate lift in thin air, and engines would struggle to produce thrust. The answer hit Johnson on the flight back to Burbank. Build a powered glider. Take a sailplane's ultra-lightweight structure and impossibly long wings, then add just enough engine to push it to altitude. Strip out everything unnecessary: pressurized crew compartments beyond the cockpit, defensive weapons, redundant systems, even conventional landing gear. Make it so light, so aerodynamically clean, that it could float at 70,000 feet like a leaf on the wind. Back at Lockheed, Johnson assembled a small team in a corner of the production facility. He needed engineers who could work fast and think unconventionally. He grabbed Dick Boehm, a structures specialist who understood exotic materials. Willis Hawkins joined for aerodynamics. For propulsion, Johnson recruited a young engineer named Ben Rich, recently graduated from UCLA, who would later succeed Johnson and become a legend himself. Johnson gave them the pitch: design an aircraft that breaks every rule in aviation engineering. They'd work in complete secrecy, isolated from Lockheed's main engineering departments. No bureaucracy, no committee meetings, no interference from corporate management or military oversight. Just a handful of engineers, a clean sheet of paper, and an impossible deadline. They worked in a rented circus tent adjacent to the main Lockheed facility because all the proper buildings were full. The tent reeked of aviation fuel and body odor. Summer temperatures inside exceeded 100 degrees. Johnson didn't care about comfort. He cared about speed and innovation. Within 3 weeks, they had preliminary drawings. The aircraft looked bizarre. A slender fuselage barely wider than a man's shoulders, wings stretching 80 feet tip to tip. A single turbojet engine mounted in the rear fuselage. It looked fragile, like something that would snap in the first strong gust of wind. Johnson called it the CL-282. The Air Force would later designate it the U-2, and every aviation expert who saw the preliminary designs said the same thing: it would never fly. Johnson needed a facility where his team could work without questions from curious Lockheed employees or Soviet spies who'd already penetrated several American aerospace companies. The main Lockheed plant in Burbank was too exposed, too visible, with workers gossiping about every new project over beers at local bars. He found his answer in a cluster of temporary buildings on the northeast side of the Burbank facility, downwind from a plastics factory that emitted nauseating fumes. The smell was so bad that workers called the area Skunk Works, borrowed from the comic strip Leo Abner, where a character operated the Skunk Works, producing an illegal beverage from skunks and old shoes. The name stuck. Johnson made it official. His Advanced Development Projects Division would forever be known as the Skunk Works. The team that gathered there in spring 1954 numbered just 23 engineers and 30 shop workers. Johnson established rules that would define Skunk Works operations for decades. No written memos. Walk across the room and talk face to face. No committees. Decisions made by whoever knew the subject best. no procurement bureaucracy. If you needed a part, you bought it that day from whoever could deliver it fastest. Most radical of all, the customer, meaning the Air Force and CIA, stayed out of the workshop. They could review progress, but they couldn't dictate engineering solutions. The design that emerged on drafting tables looked increasingly insane as engineers calculated actual numbers. The wingspan would stretch 80 feet, but the fuselage would measure only 49.5 feet long and just over 4 feet wide at its widest point. For comparison, a modern Cessna 172 trainer has a 36-foot wingspan. The U-2's wings would be more than twice as long, yet the entire aircraft would weigh barely 16,000 pounds, fueled and loaded, about the same as 2 full-size pickup trucks. Those proportions created a fundamental problem. Normal aircraft have thick, strong wings attached to a heavy fuselage that forms the structural backbone. The U-2 would essentially be all wing with a fuselage hanging underneath. The wings would need to support not just the aircraft's weight, but also massive bending loads during flight and landing. Yet they had to be feather light. Johnson's solution involved construction techniques never before used in production aircraft. The wings would be built as single-piece structures from root to tip, eliminating weight-adding joints and fasteners. Inside each wing, a single titanium spar, a beam running lengthwise, would carry primary loads. Thin aluminum ribs would maintain the wing's aerodynamic shape. The outer skin would be aluminum alloy milled to just 0.020 inches thick in places, roughly half the thickness of a credit card. Building structures that light and that large required new manufacturing methods. Lockheed machinists developed chemical milling techniques, bathing aluminum sheets in acid baths that ate away material to precise thicknesses. They hand-formed complex curved sections using wooden forms and rubber mallets. Every rivet was countersunk flush with the skin to minimize aerodynamic drag. Every seam was sealed with rubber compound to maintain smooth airflow. The fuselage presented different challenges. It needed to house the pilot, the camera bay, fuel tanks, and the engine, while remaining as light as possible. Johnson specified a semi-monocoque design. The skin itself would carry structural loads, rather than relying on an internal frame. The cockpit would be pressurized, but just barely, to 28,000-foot equivalent altitude when flying at 70,000 feet. That meant the pilot would still need a partial pressure suit, essentially a spacesuit, but it saved considerable weight compared to full sea-level pressurization. By August 1954, the design was frozen. Johnson submitted the formal proposal to the Air Force in November, pricing it at $22 million for 20 aircraft. The Air Force Procurement Office read it, thanked Johnson politely, and rejected the proposal as too risky. The Air Force rejection should have killed the project. But Trevor Gardner wasn't finished fighting. He bypassed the Air Force procurement bureaucracy entirely and went straight to the CIA. In November 1954, Gardner arranged a meeting with Richard Bissell, a brilliant economist who'd recently joined the CIA and was building the agency's technical intelligence capability. Bissell had helped administer the Marshall Plan. He understood large-scale projects, and he understood risk. Bissell looked at Johnson's proposal and saw what the Air Force had missed. This wasn't just another aircraft program. It was a potential solution to America's intelligence blindness. He took the proposal to CIA Director Allen Dulles. Within 3 weeks, Dulles presented it to President Eisenhower in the Oval Office. Eisenhower approved it immediately, with one condition: the CIA would run the program, not the Air Force. This would be a civilian intelligence operation, giving Eisenhower plausible deniability if anything went wrong. On December 9, 1954, Bissell called Johnson with authorization to build 20 aircraft for $22 million. First delivery in 8 months. Johnson hung up the phone and told his team they'd just landed the most important contract in American intelligence history. Then he told them something else. They had to figure out how to actually build the wings they'd drawn. The wing problem consumed the first 3 months of 1955. On paper, the design worked beautifully. In reality, building an 80-foot wing that could flex up to 30 feet during flight without breaking required solving problems no aircraft manufacturer had faced before. The wing needed to be stiff enough to maintain its aerodynamic shape, but flexible enough to absorb gust loads without shattering. Johnson assigned the wing structure to Dick Boehm, who attacked it like a mathematical puzzle. He calculated that at maximum operational weight, the wing tips would deflect upward nearly 6 feet from their unloaded position. During hard landings, inevitable given the aircraft's challenging handling characteristics, the wings might flex 25 feet upward. The structure needed to handle these enormous movements repeatedly without developing fatigue cracks. Boehm's solution was the single-piece wing spar made from titanium, a metal that had barely been used in aircraft before 1955. Titanium offered an incredible strength-to-weight ratio, but it was notoriously difficult to machine and weld. The spar for each wing would measure 40 feet long, taper from 8 inches deep at the root to 3 inches at the tip, and weigh just 90 pounds. Lockheed's machinists had to develop entirely new techniques for precision milling titanium, using carbide cutting tools running at precise speeds to avoid work hardening the metal. The wing skin presented an even more delicate challenge. At 0.020 inches thick, the aluminum was so thin you could dent it by pressing hard with your thumb. Workers learned to handle wing panels like porcelain, supporting them on padded racks. One careless bump could create a dent that would disrupt airflow and cost hours of repair time. Johnson installed special lighting in the assembly area so workers could see even tiny imperfections in the mirror-smooth skin. Each wing took 6 weeks to build, with 4 workers assigned full-time to a single wing. They started with the titanium spar, then built up ribs and stringers around it. Finally attaching the skin with thousands of flush-mounted rivets, every rivet hole was reamed to exact diameter, deburred by hand, and inspected before installation. The completed wing weighed 1,050 pounds, about as much as a large motorcycle, but spanning 40 feet. When workers lifted the first completed wing and attached it to the fuselage in March 1955, it flexed visibly under its own weight. Engineers watching the assembly felt their stomachs drop. The structure looked impossibly fragile, but the stress calculations held. The wing was strong enough. With wings taking shape, Johnson turned to the propulsion nightmare. The Pratt & Whitney J57 turbojet engine could theoretically operate at 70,000 feet, but theoretically and reliably were different problems. At that altitude, with air density at barely 20% of sea level, jet engines struggled to breathe. Combustion became unstable. Compressor blades stalled. Flameouts were common. Johnson needed modifications that Pratt & Whitney had never attempted. The engine would run continuously at maximum output for hours, not the brief bursts typical of fighter operations. It would operate in temperatures ranging from minus 70 degrees Fahrenheit at altitude to 120 degrees on desert runways. And it absolutely could not fail over Soviet territory, because a forced landing meant either death for the pilot or a propaganda disaster when the Soviets captured him and the aircraft. Pratt & Whitney assigned a team led by engineer Leonard Hobbs to tackle the modifications. They started with the J57P37 variant, which produced 2,500 pounds of thrust at sea level. The challenge was maintaining adequate thrust at altitude, where air density plummeted. Hobbs's team redesigned the combustion chamber to achieve stable burning in thin air, modified the fuel control system to prevent flameouts during turbulence, and added temperature sensors throughout the engine to warn of problems before catastrophic failure. The fuel system presented problems Johnson hadn't anticipated. JP7 fuel, specially formulated for high-altitude flight, needed to flow reliably at temperatures where ordinary fuel would freeze solid or boil away depending on altitude. The U-2 would carry 1,235 gallons distributed through 8 tanks in the fuselage and wings. Johnson designed a fuel feed sequence that maintained the aircraft's center of gravity as fuel burned off, critical because even minor balance changes affected the U-2's already touchy handling. But the most dangerous problem was the pilot. At 70,000 feet, atmospheric pressure drops to less than 1 pound per square inch, about 1/15 of sea level pressure. A human exposed to that environment would lose consciousness in 15 seconds and die within 2 minutes as blood literally boiled from decompression. The cockpit pressurization system could maintain only 28,000-foot equivalent pressure, still high enough to cause hypoxia without supplemental oxygen. Johnson worked with David Clark Company to develop a full-pressure suit for U-2 pilots. The MC-2 suit was essentially a spacesuit with an airtight rubber bladder inside a nylon restraint layer. The helmet sealed to the suit with a locking ring. If cockpit pressure failed, the suit would automatically inflate, maintaining 35,000-foot equivalent pressure around the pilot's body. But flying in a pressure suit was exhausting. Pilots fought the suit's resistance to every movement. During training flights, pilots lost 5 to 8 pounds in sweat during a single mission. The cockpit itself measured just 32 inches wide. Johnson eliminated every non-essential instrument and control to save weight. There was no autopilot, no radar, no defensive weapons, just flight instruments, camera controls, and a drift sight, a simple optical device for the pilot to track ground position. The canopy was a single-piece acrylic bubble offering excellent visibility, but no ejection seat compatibility. If something went catastrophically wrong at altitude, the pilot would need to manually bail out, diving through thin air for 40,000 feet before deploying his parachute in breathable atmosphere. In June 1955, with the first aircraft nearly complete, Johnson conducted a ground engine test at Burbank. The J-57 roared to life, producing thrust readings that matched predictions. But when mechanics tried to shut it down using standard procedures, the engine refused to quit. It kept running for 7 minutes before finally spooling down, melting turbine blades and destroying thousands of dollars in components. Johnson went back to Pratt & Whitney. They fixed the shutdown sequence. The engine modifications took another month. On August 1, 1955, the first U-2 sat on a remote lake bed in Nevada called Groom Lake, later famous as Area 51. Johnson had chosen the location for its isolation, miles from prying eyes, with a smooth, dry lake bed perfect for emergency landings. The aircraft looked even more bizarre in full daylight than it had in the Skunk Works assembly building. The wings drooped noticeably when the aircraft sat on the ground, their tips sagging nearly 2 feet below horizontal. Lockheed test pilot Tony Levier climbed into the cockpit wearing the MC-2 pressure suit, which crinkled and hissed as he moved. Levier was 40 years old, a veteran who'd first flown dozens of experimental aircraft. He'd seen strange designs before, but nothing prepared him for the U-2's handling characteristics during taxi tests. The U-2 used a bizarre landing gear arrangement to save weight. The main gear was a bicycle configuration, 2 wheels in tandem along the fuselage centerline, with small detachable outrigger wheels under each wing that would fall away after takeoff. On the ground, the aircraft balanced precariously. Levier later described it as riding a very tall unicycle while wearing a spacesuit. Johnson had only authorized taxi tests that day, not flight. But as Levier accelerated down the lake bed at 70 knots, the U-2 lifted off spontaneously. The wings generated so much lift and ground effect that the aircraft jumped into the air at a speed 20 knots below what Johnson calculated as takeoff velocity. Levier found himself airborne, unprepared, in an aircraft that had never flown. He climbed to 300 feet and circled the lake bed for 15 minutes testing controls. The U-2 flew smoothly, but responded sluggishly to control inputs. Those enormous wings made the aircraft stable but ponderous. When Levier attempted to land, disaster nearly struck. The long wings created so much lift that the aircraft didn't want to descend. Levier had to force the nose down aggressively, then flare at the last second. The U-2 touched down hard on the rear wheel, bounced 15 feet back into the air, came down again on the front wheel, and skipped twice more before finally staying on the ground. The landing gear collapsed. The fuselage scraped along the lake bed in a shower of sparks and dust before sliding to a stop. Levier sat in the cockpit, shaken but unhurt. Johnson ran across the lake bed, expecting to find his aircraft destroyed. Instead, he found only minor damage to the landing gear attachment points and some scraped belly skin. The fundamental structure had survived intact. They'd fix it and fly again. Over the next 3 months, test flights revealed the U-2's peculiar personality. It was stable in cruise, but demanding during takeoff and landing. The operational envelope was incredibly narrow. At 70,000 feet, the speed margin between stalling and exceeding maximum velocity was just 10 knots. Fly too slow, and the aircraft would stall and potentially enter an unrecoverable spin. Fly too fast, and aerodynamic forces could tear the fragile wings off. Pilots called it coffin corner, and flying the U-2 meant living in that corner for hours at a time. On September 17, 1955, test pilot Robert Seeker took off for a high-altitude test. At 52,000 feet, a control malfunction sent the U-2 into an inverted spin. Seeker fought the controls as the aircraft tumbled earthward, finally regaining control at 23,000 feet. He landed with the aircraft structurally damaged but flyable. Then, in April 1956, pilot Frank Grace wasn't as lucky. His U-2 experienced engine failure at altitude during a training flight. Grace attempted to glide to a landing, but misjudged his approach. The aircraft stalled 50 feet above the runway and dropped like a stone. Grace died on impact. 5 months later, pilot Howard Carey crashed during landing practice, killed instantly. Despite the crashes, the CIA pushed forward. Richard Bissell didn't have the luxury of extended testing. Soviet bomber production continued every day the U-2 remained grounded. In November 1956, Bissell activated Detachment A, a unit of CIA pilots operating from Incirlik Air Base in Turkey. The pilots were officially sheep-dipped, resigned from the Air Force, and hired as Lockheed civilians to maintain plausible deniability. They earned $2,500 per month, more than triple their military salaries. The pilots underwent intensive training at Groom Lake. They learned to fly the U-2 from the right seat. Johnson had placed the pilot off-center to accommodate cameras in the left fuselage bay. They practiced navigation using only a drift sight and watch, since radio transmissions would reveal their position. Most critically, they learned to operate while imprisoned in the pressure suit for missions lasting 9 hours or more. Hervey Stockman, a former Air Force captain, flew one of the first operational missions on June 20, 1956. His route took him from Wiesbaden, Germany, across East Germany and Poland. The cameras captured every Soviet military installation along a corridor 125 miles wide. When CIA photo interpreters developed the film, they could read vehicle license plates from 70,000 feet. They could identify aircraft types on runways. They could count individual bombers. Emboldened by success, Bissell authorized deeper penetrations. On July 4, 1956, Independence Day, deliberately chosen for symbolic impact, pilot Carmine Vito took off from Wiesbaden on the most audacious intelligence mission of the Cold War. His flight plan took him directly over Leningrad, then Moscow, then south to Ukraine, before exiting Soviet airspace near the Black Sea. Total distance, 2,900 miles deep in Soviet territory. Flight time, 8 hours, 45 minutes. Vito climbed to 72,000 feet and crossed into Soviet airspace at 0900 hours local time. Soviet radar operators detected him immediately. Air defense commanders scrambled every available interceptor. MiG-17s, MiG-19s, even experimental MiG-21 prototypes. Dozens of fighters climbed desperately, pilots pushing their aircraft to service ceilings and beyond. The MiG-19s topped out at 58,000 feet, nearly 3 miles below Vito's altitude. Soviet pilots could see the U-2's contrail streaking across the sky above them, a white line mocking their impotence. They couldn't reach him. Surface-to-air missile batteries fired 14 missiles at the U-2, As it passed over military installations, every missile detonated harmlessly thousands of feet below its target. The SA-1 Guild missiles lacked the range to reach 72,000 feet. Soviet air defense had been rendered completely irrelevant by Johnson's design. Vito's cameras captured stunning intelligence. Photos showed the Philly airframe plant, where Myasishchev M4 strategic bombers were assembled. They revealed that Soviet bomber production was far below Pentagon estimates. There was no bomber gap, no massive Soviet advantage. The photos also captured new fighter designs, missile test facilities, and naval shipyards. In one 8-hour mission, Vito collected more intelligence than the CIA had gathered from all other sources in the previous 2 years. But the mission had consequences. Soviet Premier Nikita Khrushchev was informed within hours that an American aircraft had violated Soviet airspace with impunity, overflying the capital while Soviet defenses watched helplessly. Khrushchev was enraged. He immediately lodged a secret diplomatic protest with the U.S. State Department, threatening retaliation if the flights continued. Eisenhower faced a dilemma. The intelligence was invaluable. It proved the bomber gap was fiction, possibly preventing a massive and unnecessary military buildup. But continuing the flights risked war. Eisenhower authorized continued missions, but imposed strict controls. Every flight required his personal approval. Bissell could propose missions. Only the president could authorize them. Through 1956 and 1957, U-2s flew 22 more missions over the Soviet Union, each one mapping Soviet military capabilities in unprecedented detail. Khrushchev protested privately after every flight, but never acknowledged the violations publicly. Doing so would mean admitting Soviet defenses were powerless. By 1960, the U-2 program had collected thousands of intelligence photographs, but Soviet technology was catching up. The SA-2 Guidelines surface-to-air missile, introduced in 1957, could theoretically reach 70,000 feet. Soviet radar networks had improved, tracking U-2 flights with increasing accuracy. CIA analysts warned that the immunity period was ending. Still, the intelligence was too valuable to stop. Francis Gary Powers was 30 years old, a former Air Force pilot who joined the CIA U-2 program in 1956. On the morning of May 1, 1960, Powers prepared for Mission 4154, a flight from Peshawar, Pakistan, across the Soviet Union to Bodø, Norway. The route would photograph new Soviet ICBM sites, strategic bomber bases, and suspected nuclear weapons facilities. It was perhaps the most important intelligence mission of the Cold War. Powers took off at 0600 hours and climbed to 66,000 feet as he crossed into Soviet airspace near the Afghan border. Soviet radar picked him up immediately. Air defense commanders had been preparing for this moment for 4 years. They'd studied U-2 flight patterns, analyzed weaknesses, and developed new tactics. This time, they were ready. As Powers approached Sverdlovsk at 0853 hours, 14 SA-2 missile batteries formed a defensive gauntlet along his flight path. The missiles launched in coordinated salvos, their trajectories calculated to intercept, even if Powers changed course. Powers saw the first missile streak past his canopy, missing by 300 feet. The second missile detonated 100 feet behind the aircraft. The explosion didn't hit the U-2 directly, but it didn't need to. The blast wave slammed into the fragile airframe with the force of a wrecking ball. Those ultra-thin wing panels that had saved so much weight now became a liability. The wings buckled, control cables snapped, the tail section separated from the fuselage. Powers found himself tumbling through thin air at 66,000 feet in an aircraft breaking apart around him. He tried to activate the ejection seat, but couldn't reach the handle as G-forces pinned him against the canopy. The destruct switches, designed to destroy the camera equipment and classified systems, were similarly unreachable. Powers made a split-second decision: manually bail out. He released his seatbelt, the only thing holding him in the disintegrating aircraft, and was immediately sucked out into the slipstream. Powers free fell for nearly 9 miles before deploying his parachute at 15,000 feet. Soviet farmers watched him descend into a field near Sverdlovsk. KGB officers arrested him within minutes. The wreckage of the U-2 scattered across several square miles, but key components survived intact: the cameras, the film, enough fragments for Soviet engineers to analyze Johnson's design secrets. The diplomatic explosion exceeded the physical one. Khrushchev had caught the Americans red-handed conducting espionage. For 4 years, the U.S. had maintained plausible deniability, but Powers and the wreckage provided undeniable proof. Khrushchev revealed the capture at a Paris summit with Eisenhower on May 16th, humiliating the American president who'd initially claimed the U-2 was a weather research aircraft that had strayed off course. The Eisenhower administration scrambled to explain. NASA had prepared a cover story about high-altitude weather research, but Khrushchev demolished it by displaying Powers and the wreckage in Moscow. The incident destroyed a planned summit between Eisenhower and Khrushchev, poisoned U.S.-Soviet relations, and ended Eisenhower's presidency under a cloud of embarrassment. Powers was tried for espionage in Moscow, sentenced to 10 years in prison, but exchanged for Soviet KGB Colonel Rudolf Abel. In February 1962, he returned to America not as a hero but under suspicion. Some critics claimed he should have activated the destruct system or committed suicide rather than be captured. The U-2 overflights of the Soviet Union ended permanently on May 1, 1960. But the aircraft itself had proven Kelly Johnson's design philosophy beyond any doubt. It had achieved the impossible mission. The Powers incident should have ended the U-2's operational life, but Kelly Johnson's design was too valuable to retire. While Soviet air defenses could now reach 70,000 feet, most of the world remained vulnerable to high-altitude reconnaissance. The U-2 found new missions over Cuba, China, Vietnam, and the Middle East. During the Cuban Missile Crisis in October 1962, U-2 photographs of Soviet missile sites gave President Kennedy the intelligence he needed to navigate the most dangerous confrontation of the Cold War. Major Rudolf Anderson flew one of those Cuban missions on October 27, 1962. A Soviet SA-2 missile shot him down over eastern Cuba, killing him instantly, the only U.S. combat fatality of the missile crisis. But his photographs and those from other U-2 flights proved Soviet missiles were operational in Cuba, validating Kennedy's naval blockade and ultimately forcing their removal. The aircraft kept evolving. Lockheed developed the U-2R in 1967, essentially a new aircraft with 40% more wing area and twice the payload capacity of the original. The cockpit was widened, the engine upgraded to a more powerful Pratt & Whitney J75. The new version could fly longer missions carrying heavier sensors. In 1994, Lockheed updated the design again with the U-2S, installing a General Electric F-118 engine and modern avionics. That version still flies today. More than 70 years after Johnson's original design, the U-2 has flown reconnaissance missions in every major conflict since 1956. It monitored North Vietnamese supply lines along the Ho Chi Minh Trail. It tracked Soviet naval movements during the Cold War. It provided intelligence during both Gulf Wars, operations in Afghanistan, and ongoing missions that remain classified. NASA operates 2 U-2s for scientific research, studying atmospheric chemistry, testing sensors, and monitoring environmental changes. What makes the longevity remarkable is that Johnson designed the U-2 in 1954 using slide rules and wind tunnels. No computers, no computational fluid dynamics, just fundamental aeronautical engineering combined with radical thinking about what an aircraft could be. The U-2 proved that sometimes the best solution to an impossible problem is to throw out conventional wisdom entirely. Johnson's design philosophy, forged during the U-2 program, became doctrine at the Skunk Works. Small teams, minimal bureaucracy, direct communication between engineers and customers, rapid prototyping, emphasis on performance over comfort. That philosophy produced the SR-71 Blackbird, which flew at Mach 3.2 and replaced the U-2 for some missions. It produced the F-117 Nighthawk stealth fighter. It influenced every advanced aircraft program since. Johnson retired from Lockheed in 1975 as a legend, recipient of the Medal of Freedom, holder of the Collier Trophy, with his name on 40 patents. He died in 1990 at age 80, but his U-2 kept flying. Pilots who fly the U-2 today, they call themselves Dragon Ladies after the aircraft's official name, operate an aircraft that would be recognizable to the pilots of Detachment A in 1956. The basic airframe is unchanged. The handling characteristics remain demanding. The mission profile is identical. Climb to extreme altitude, fly long-duration reconnaissance missions, fight the aircraft back to the ground. The U-2 was supposed to fly for maybe 5 years before Soviet defenses caught up. It's now flown operational missions for nearly 70 years. And the Air Force projects it will remain in service until at least 2030. Kelly Johnson's impossible airplane has outlasted the Soviet Union it was built to spy on, outlasted the Cold War, outlasted every aircraft designed to replace it. In aviation museums, you can see P-38s and F-80s, aircraft Johnson designed that are now historical artifacts. But walk onto any number of military air bases, and you might see a U-2 taxiing for takeoff, its wings flexing, its pilot sealed in a pressure suit, climbing toward the edge of space to continue a mission that began in a stinking tent in Burbank. When one engineer refused to accept that something was impossible,